Okay, and then we did the drawbacks of Rutherford model of atom, right? Now today we are going to go to the next topic, which is electromagnetic radiation. What do we understand by electromagnetic radiation? It is the radiation which is simultaneously subjected to electric and magnetic fields, right? So any radiation which is simultaneously subjected to an electric field and kept in a magnetic field, they are known as electromagnetic radiations. Now in this we say that the electric and the magnetic fields, they are perpendicular to each other, and also they are perpendicular to the propagation of the wave. If the direction in which the wave is traveling, that is perpendicular to the electric field as well as the magnetic field, as you can see here in the diagram. Okay, so as you can see here in the diagram, it is simultaneously, it has the electric and the magnetic field which all are running perpendicular to each other. Now if you are doing the characteristics of radiations, electromagnetic radiations, what do we say? Characteristics number 1, all electromagnetic radiations are perpendicular to each other. That is, they are perpendicular to the electric field, they are perpendicular to the magnetic field, and it is also, the propagation of the wave is also perpendicular, right? And secondly, all electromagnetic waves, they travel with the speed of light, that is 3 into 10 raised to power 8 meters per second. Okay, and also electromagnetic radiations do not need a material medium to propagate. Do not need a material medium to propagate, right? Or in other words, what do we say? That they can also travel in vacuum. When we are talking of any electromagnetic wave, they are characterized by the following measurements. Let's say this is one fixed point, okay, and or we can say that this is the source of electromagnetic radiation. Over here, when the electromagnetic radiation is visualized, the propagation of the electromagnetic radiation is something like this. In a similar manner, as you have tied a rope on this fixed point and you give it a jerk. When you give a jerk, the pattern which would be seen would be something like this. That is what electromagnetic radiations are. Okay. Now when we are looking at the measurements which we do for the electromagnetic radiation, the first one, that is known as wavelength. Wavelength is given by lambda. Okay, what is wavelength? It is the distance between two crests. Crest is the upward displacement of the wave and trough is the downward displacement of the wave. So distance between two crests or distance between two troughs, that is known as lambda. Right? So what are we saying? What is lambda? It is distance between two crests or two troughs. That is known as lambda or the wavelength. The unit, because it is a distance, so the unit which is used is meters, but meter is a very big unit to measure this, so we use smaller units like angstroms. 1 angstrom, that is equal to 1 into 10 raised to power minus 10 meters, right? Or we use picometer. 1 picometer, that is equal to 10 raised to power minus 12 meters. We can use nanometer. 1 into 10 raised to power minus 9 meters. So generally the units which we are going to use to measure wavelength, they are going to be these, right? Then the second characteristic is frequency. The second characteristic which we are going to study, that is frequency. Frequency is denoted by nu, and frequency, that is the number of cycles the wave takes in 1 second. The number of cycles the wave takes in 1 second, that is frequency. The unit which we used over here is per second, or also we use another unit which is hertz. Okay? Then the third characteristic is velocity of light. As we just said that the electromagnetic radiations, they have the same velocity, that is velocity of light, and velocity of light has a fixed value, that is 3 into 10 raised to power 8 meters per second, and it is denoted by small c. So we have done 3 characteristics over here. Let's look at the relationship between 3. When we are looking at the relationship between lambda, frequency and velocity of light, we say that lambda, that is equal to c upon nu. Right? So you can see over here that the wavelength is inversely proportional to frequency. Okay? So what is the relationship? Lambda, that is equal to c upon nu. Then the fourth characteristic we have is wave number. Wave number, that is represented by u bar, and it is the reciprocal of wavelength, right? So we will have the unit of wave number as per meters. Per meter, that is going to be the unit. Okay, then after wave number we have another characteristic which is known as amplitude. Another characteristic which we have, that is amplitude. Amplitude is denoted by A, and it is the height of the crest or depth of the trough, right? It is the height of the crest or depth of the trough. This is also measured in, this is going to be measured in meters. It has, because it is the distance, so it has the same unit as what? As the wavelength, right? And then after that, we have another this thing which is known as time period. Time period is denoted by T, and it is the time taken for the cycle to complete, time taken for the wavelength complete one cycle. Right? Time taken for the wavelength to complete one cycle, and mathematically time period is given by 1 upon frequency. It is the reciprocal of frequency. Right? So how many? We've done 6 characteristics of a wave. The first one is lambda, wavelength, distance between 2 crests or 2 troughs. The second one is frequency, number of cycles the wave takes in 1 second. Then the velocity of light. Velocity of light, whether we are talking of in material medium or we are talking of vacuum, it has the same value. There is very slight difference in vacuum, travels with the speed of 2.8 to 2.9. So it is almost the same speed. Then the relationship, this is important because this would be used for the lambda that is equal to c upon nu. Then the wave number that is equal to 1 upon lambda. Then the amplitude, that is the height of the crest or depth of the trough. And the time period. Again, time period is important because we might get this expression in one of the questions, the numericals which we are going to solve for this section. So time period that is equal to time taken for the wavelength to complete one cycle. Okay. Now after doing this, we know what electromagnetic radiation is. So electromagnetic radiations, they are characterized mainly by 2 things. One is the lambda and the other one, that is frequency. Okay, so let's go on to arrangement of electromagnetic radiations. They are not one electromagnetic radiation, but there are several electromagnetic radiations which are arranged in order of increasing frequencies or increasing wavelengths, either of the two. So let's go on to the next topic, which is electromagnetic spectrum. Electromagnetic spectrum. What do we understand by electromagnetic spectrum? Electromagnetic spectrum is the arrangement of electromagnetic radiations, in order of their decreasing frequencies or increasing wavelengths. Right? In order of decreasing frequencies or increasing wavelengths, that is what electromagnetic spectrum is. So if we are looking at the arrangement, let's see how we can talk of the arrangement of electromagnetic radiations. The one which has the lowest wavelength, right? The one which has the lowest wavelength, let's keep it over here. And we are saying that lambda over here is increasing. That is, it is going from 10 raised to power minus 11 to 10 raised to power 3. Right? So what are we saying? Decreasing frequencies or increasing wavelengths. So frequency that has to decrease, the frequency will decrease. So frequency that is decreasing from 3 into 10 raised to power 21 to 3 into 10 raised to power 7. Okay, so this is the order. Now when we are talking of the wavelength of the electromagnetic radiation with lowest wavelength, in some of the books cosmic rays is given, but according to the new concept, the one which has the lowest wavelength, that is gamma rays. Okay, so one which we are going to have the lowest wavelength, that is the gamma rays. Then after that is the X-rays, and after X-rays we have the UV region, that is the ultraviolet region, and then we have the visible region. This is one of the important regions because this is all what we can see. The visible region. Visible region consists of different colors representing the colors of a rainbow, that is Vibgyor. Right? And Vibgyor means what? Violet, indigo, blue, green, yellow, orange and red. That is what Vibgyor is. It approximately starts from 400 nanometers and ends up to 700 nanometers. Right? So violet has 400 and it keeps on increasing from violet to red. Then after visible region is the infrared region. Infrared region. After the infrared we come to microwaves. And then the radio waves. Right? Now we have to remember over here that radio waves, they have low energy. The radio waves have low energy, but what happens to the wavelength over here? They have long wavelength. The wavelength of this side is long wavelength, and also they have very high frequencies. We are going from 3 raised to power, low frequency. We are going from 3 into 10 raised to power 21 to 3 into 10 raised to power 7. So they are going to have low frequencies, right? Whereas when we are talking of gamma rays, they are rays of high energy. High energy, they have short wavelength, and they have frequencies are also going to be high frequencies. So in the electromagnetic spectrum, what we can see is that we are traveling from high energy to low energy, we are traveling from short wavelength to long wavelength, and we are traveling from high frequencies to low frequencies. The radio waves also, they have two types of radio waves. We say one is short radio waves and the other one is long radio waves. So the short radio waves, they are going to have lower energy with respect to long radio waves. Okay? So this is what the electromagnetic spectrum is. Basically, what do we understand by the term spectrum? We are using one word over here which is spectrum. So what is spectrum? Spectrum is the dispersion of light. Right? Dispersion of light means that whenever a light is going to go from a rarer medium to a denser medium, it is going to split. So that is what a spectrum is. So in the next section, we are going to study a little more detail of what spectrum means. Right? So let's understand what do we understand by the term spectrum. Spectrum is the splitting up of white light into series of colored bands. Colored bands or colored lines, that is what a spectrum is. Because when we are talking of an atom, when we are talking of the spectrum of atom, it is going to give a series of colored lines. But when we are talking of spectrum of a molecule, it is going to give us colored bands. Right? So that is what a spectrum is. Now spectrum is broadly classified into two. The first one, it is known as emission spectrum. Emission spectrum. What happens in emission spectrum is that the emission spectrum, it gives us bright colored lights, or we can say it gives us bright lines, okay, and the background over here is dark. So emission spectrum, it is giving us bright lines on a dark background, right? And emission spectrum is obtained when radiations emitted by the excited substance, there we've taken a source of light, we help that source of light to pass through a prism, right? When it passes through a prism and we put a screen, then we see that there are various bright lines which are coming on a dark screen. So that is what an emission spectrum is. So how it is formed, it is obtained when radiations emitted by excited substance are analyzed with the help of a spectrometer or spectroscope. Spectroscope is a device to analyze the spectrum. Okay, whereas the second type we have is absorption spectrum. As the word over here is suggesting, absorption means that we are giving a source of white light. That source of white light is first passed through a medium. That medium may be gas or it may be a solution. So what that solution does is, the solution that is going to absorb certain radiations, right? Now if it is absorbing radiations from the visible region, then in this case we do not get a colored spectrum, right? They are going to be dark lines. Okay, so in absorption spectrum we say that it gives dark lines on a bright background. Dark lines on a bright background. So this is the difference also between the two. And as I just said that in absorption spectrum, the white light is first absorbed and then emitted. Whereas in emission spectrum, the light is emitted, passed through a prism, and whatever we get, that is analyzed with the help of a spectroscope, and on screen we see bright or colored lines on a, you can say on a dark background, right? So the emission and the absorption spectrum, they can be shown as it is shown in the figure. We can see over here that the bright lines, the colored lines, they can be seen on the emission spectrum, and the dark lines, they are seen in the absorption spectrum. Okay, now when we are doing the emission spectrum is further classified into two. Right, so we are saying that the emission spectrum is classified into two. The first one is known as continuous spectrum. What do we understand by continuous spectrum? Over here, the light which we are going to take, a source of light, source of white light. This white light in continuous spectrum, we see that this white light, that when it is passed through a prism, it is going to give us the colors of the rainbow. That is, we are getting a spectrum with all the 7 colors of the rainbow with pure. Okay, so violet, indigo, blue, green, yellow, orange and red. In this case, when we are coming at the interface of two colors, the violet, that is going to merge with indigo, indigo is going to merge with blue, blue is going to merge with green, green with yellow, yellow with orange and orange with red. So there is a continuous spectrum, we cannot see any gap between the colors. That is why it is known as continuous spectrum. Okay, when one color merges into other, that is what pure is, just like that of a rainbow. The second type of spectrum which we have, that is known as a discontinuous or line spectrum. It is known as a discontinuous or line spectrum. Now in this case, the source taken is not the white light, not the sun, but the source taken over here may be gas or vapors of a liquid, right? So when we are taking the vapors of a chemical substance, we heat it in a flame or in an electric arc, right? And then after that, the radiations which are emitted by heating these in chemical substances in electric arc or in what we are saying, or in heat, we are heating them. So the radiations which are emitted, they are analyzed in this continuous spectrum. So when we are talking of this continuous spectrum, we say that the light which is emitted is passed through the prism. Is passed through the prism, and we see that there are specific lines observed. These lines are mostly bright lines because it's an emission spectrum. So we observe bright lines in the visible region. For example, when we're talking of sodium, we take the vapors of sodium, and those vapors of sodium, the radiations which they emit, they are passed through the prism. We see yellow lines at a, you can say, wavelength of 580 to 589 nanometers, right? So every atom over here, because we are analyzing atoms over here, we are not taking any source of light. So every atom over here has their own specific spectrum. Okay, so that is the reason why these are also known as thumbprints, right? They are also known as thumbprints of every atom, because every atom have their own spectrum, and by analyzing the spectrum we can qualitatively analyze what the atom is. Okay, sodium is going to give us a different spectrum. When we are talking of helium, it is going to give us a different spectrum, or we are talking of say lithium, that is going to give us a different spectrum. So every atom gives a different spectrum. A very good example of emission spectrum which was studied for the first time, the first emission spectrum which was studied, that was of hydrogen. So we will study today the spectrum of hydrogen, right? So when we are studying the spectrum of hydrogen, we say that hydrogen is an example of emission spectrum. Okay, so as I just told you, it was one of the first, we say the first spectrum which was analyzed. Okay, now when we are talking of hydrogen, what we do over here is that we take an electric discharge. This electric discharge is passed through hydrogen gas. And we see a blue radiation, blue colored radiation, or a blue light which is emitted. This blue light is passed through a prism. Okay, and when this blue light passes through a prism, a series of light or series of lines, not light, series of lines were observed. So the hydrogen spectrum, one by one the scientists started studying them, and one by one, depending upon the transition. What do we understand by transition? That how the electron is jumping from a lower energy level to a higher energy level, and then it falls back to the lower energy level. Okay, so when it is falling back to the lower energy level, it emits radiations. And and that is how a series of lines were given. Depending upon these transitions, various scientists gave different series, and those series are named on the names of the scientist itself. Like the first series which we had was Lyman series. Lyman series. Now for Lyman series, we say that the transition is from, let's say this is the first shell, N1, right? So N1 over here, that is equal to 1, and the value of N2 can be anything greater than 1. So it can be 2, 3, 4 or anything. Now what is happening over here is, we are saying that the electron jumps from the first to the next level and then it jumps back to the first level. During its jumping back to the first level, it emits radiations. And those radiations fall in the various region of the electromagnetic spectrum. As for example, when we are talking of Lyman series, we say that they fall in the UV radiation, right? It falls in the UV region. Okay, then the second series was Balmer series. Balmer series, for Balmer series, N1 that is equal to 2 and N2 that is equal to 3, 4, 5 and so on. And Balmer series is the only series which falls in the visible region. It is the only series which falls in the visible region. Okay, फिर उसके बाद the next one which we have, that is the Paston series. For that N1 that is equal to 3 and N2 is equal to 4, 5, 6 and so on. This falls in the infrared region of the electromagnetic spectrum. Then we have the bracket. For bracket N1 that is equal to 4 and N2 is anything greater than 4, 5, 6, 7 and so on. This also falls in the infrared region of the electromagnetic spectrum, right? And then we have fun. They all are after the name of the scientists, okay? And for this N1 that is going to be equal to 5 and N2 is equal to 6, 7, 8 and so on. This also falls in the infrared region, right? And then we have another series which is known as Humphrey. For Humphrey, N1 that is going to be equal to 6 and N2 is equal to 7, 8, 9 and so on, and this also falls in the higher region. Okay, now to understand that how do we get the wavelength from the series so as to calculate where it is lying in the electromagnetic spectrum. There was a scientist by the name of Riggs who gave us a mathematical expression, right? So for that, what was the mathematical expression for this? It was given as mu bar is equal to 1 by lambda is equal to 109677 1 upon n1 square minus 1 upon n2 square, where n1 is the initial shell in which the electron is present and n2 is the final shell. For Balmer series specifically, 1 upon lambda that is equal to 109677 1 upon 2 square minus 1 upon n2 square, because for Balmer the value of n1 that is going to be equal to 2, right? So there were various transitions given. One thing which you have to remember over here is the first initial 4 transitions of the Balmer series, so that by easier for you. Right? So let's see the first 4 transitions of Balmer series. Right? The first transition is from N2 is equal to 3 to N1 is equal to 2. Right? This transition, this is specifically for hydrogen atom. So the first transition that can be named as H alpha. Okay, and this is the first line. Right? This is the first line. For this, the wave number, this is the direct calculation which has been done. The wave number that comes to 5R upon 36. Okay, the calculation done is by the same formula, 1 upon lambda mu bar is equal to R, which is a Rydberg constant, which has a value of 109677. Okay, so R into 1 upon N1 square minus 1 upon N2 square. So when you calculate that, it comes to 5 upon 36 R for the first line, H alpha. Okay, and the lambda for this comes to approximately 6563, and the region in which it falls, it is the red region of Whitgill. So this table helps you to directly solve the questions for your MCQs rather than doing the entire calculation. Okay, then second transition which we are going to do, that is N2 is equal to 4 to N1 is equal to 2. For Balmer series, N1 is always going to be equal to 2. And this transition, that is represented by H beta. This is the second line. Okay. For this mu bar that comes to 3R upon 16. Right? U bar comes to 3R upon 16, and the lambda is of the order of 4861. Right? And these radiations they are giving in Angstroms. 6563 Angstroms, 4861 Angstroms, and the color which we observe over here is going to be blue. Okay? Then the third transition is from N2 is equal to 5 to N1 is equal to 2. Okay, and this is known as H gamma. This is the third line, and mu bar for this is 21R upon 100. R upon 100, and lambda for this transition is 4340. And the color which we observe is going to be indigo. Okay, then the next one is from N2 is equal to 6 to N1 is equal to 2. This is the fourth line, H delta. Fourth line. Okay, and mu bar for this is 8R upon 36. R upon 36, and lambda is 4102 angstrom. Right? And the color which we are going to observe over here is violet. Right? So we are seeing over here then in the hydrogen spectrum, we are getting colors violet, indigo, blue and red. Got it? So these are a little introduction about the hydrogen spectrum. We will do a little more when we will do the Bohr's model. Okay? So today we will do till here.